So our next point is Galerkin method. Now in this method you have to make use of a weighted function, trial function. So let's see what it is. So now the another name for Galerkin method is weighted residual method. So it is also known as weighted residual method. So basically what happens in this method is you have to consider one trial function. You have to consider any function and that function is denoted by t or t of x. Okay, so now this function, you have to consider this function such that it should satisfy the boundary condition, and most of the time you will be asked boundary value problems. That means only boundary condition will be given and they won't give you the initial 2 3 conditions. You'll be directly given if the interval is from 0 to 1, then you will be given value of y at x equals to 0, that is y naught, and they'll directly give you value of y at x equals to 1. So these are known as boundary value conditions or boundary value problems. So you have to consider one trial function such that it should satisfy boundary values or boundary conditions. Now if you have to substitute this trial function in the given differential equation, so you'll be given some differential equation, that is y, suppose for example y double dash plus y dash plus x equals to 0. So this is given differential equation. You need to substitute this trial function in this equation. So this will be resulted as t double dash plus t dash plus x equals to 0. So this is after substitution of trial function in the given differential equation. So now when you substitute the given trial function uh, in the given differential equation, this value is known as residue or residual. So this is what residual is after substitution of trial function in the given differential equation. So this is residual. Now what we are going to do is we will consider one weight function. So weight function is denoted by, so weight function is denoted by wi. It will be w1, w2 up to so on, and we have to take product of this residual function. It is denoted by r. So you have to take my product of r into wi. Okay, so rx into wx, and then you need to integrate it. So integrating over the domain, so whatever the domain is, that is the range of x, you need to integrate over that. So suppose it's from x0 to xn, where x0 and xn are the boundary conditions for x. So you need to integrate over that and integrate for rx into wx, and then this integration you need to equate it with 0. So now with the help of this you will get some system of equation, and after solving those system of linear equation you will get to know the unknown parameters or unknown quantities, for example alpha I, that is alpha 1, alpha 2, so that you can substitute this alpha 1, alpha 2 into the trial function and you'll get the exact required function, and this is known as Galerkin method or weighted residual method. Now this is most important part or ingredient of finite element method. This is not in your syllabus, it is just for your information. So finite element method. And another one is spectral method. Okay, so now Let's see one generalized form of what the equations are. So suppose you are given a differential equation. It is in the form of y double dash plus p of x into y dash plus q of x into um, y equals to f of x. Okay, so this is the given differential equation and x ranges from a to b. Then boundary condition is also given. So suppose this boundary condition is p naught of y of a plus q naught of y dash of a equals to r naught and p1 of y of b plus q1 of y dash of b equals to r1. Basically they are just initial conditions, so in an example you'll get to know what exactly it is. So now we have to consider one trial function, so it is t of x equal to, now this trial function is in the form of some parameter or unknown variable, that is alpha I into phi I of x. Okay, so this is the form of every trial function. So I goes from 1 to n, the summation is over, I goes from 1 to n. Now this is another representation, that is I equals to 1 to n of alpha I into wi of x. Now this wi of x is known as base function. So this is the base function. So we need to substitute this trial function in the given differential equation, and thus we will get, instead of y you have to put t, so t double dash plus p of x into t dash plus q of x t equals to f of x. Okay, so now this whatever we have substituted, you have to consider this as residual function, that is r of x. So this will be equal to this entire function, so you have to take this f of x to LHS. So you'll get t double dash plus p of x t dash plus q of x into t minus f of x. So this is your residual function. Now you have to integrate I over, that is integrate this residual function into wx dx, and you have to equate it with 0 along with the integration is taken along the boundary points of the given differential equation. First example is you have to use Galerkin method and compute the value of y of 0.5, and the boundary value problem is defined by y double dash plus y plus x equals to 0, and the range is from 0 to x goes from 0 to 1. So the boundary condition is y of 0 equals to y of 1, which is equal to 0. Okay, so now first what we are going to take is a trial function. So let t of x equals to summation I goes from 1 to n alpha I wi of x. Now we need to take any w or wi of x such that it should satisfy the boundary condition. So suppose if we consider it as x raised to I into 1 minus x, then w1 of x will be x into 1 minus x, and w2 of x equals to x square into 1 minus x. So if we substitute the boundary condition, that is x equals to 0, then you'll get 0 into 1 minus 0, so 0. So it equals to y value at value of x at y, so this is 0. So it satisfies the boundary condition. Similarly, if you consider x equals to 1, then you'll get 1 minus 1 is 0. So again value becomes 0, and that's what required. Similarly, for w2 of x, you'll have to consider if 0 is value of x is 0, then this entire becomes 0. This is satisfied. Similarly, for x equals to 1, 1 minus 1 is 0. So again the value becomes 0. So both w1 and w2 of x satisfies the boundary condition. So you can continue with this process. Another way of solving this Galerkin method is where you can calculate w1 and w2 simultaneously. You don't have to suppose that, so there is a guarantee there. So we'll solve by both the methods. Actually both are Galerkin methods, but the way is slightly different, so we'll see both of them. So now w1 and w2 are we have taken over there. Now t of x is nothing but alpha 1 into w1 of x. So this will be equal to what? So alpha 1 as it is, what is w1 of x? It is x into 1 minus x. So now at x equals to 0, what are the conditions for t? So this is t of x, trial condition. So for x equals to 0, t becomes 0, and for x equals to 1, t also becomes 0. Okay, so these are the conditions for t with respect to x, boundary conditions for x. Now we have to find residual function. So r of x is nothing but substitution of the trial function into the given differential equation. So this will give you t double dash plus t plus x. Okay, now we need to integrate this integral. Now what are the conditions for x? X goes from 0 to 1. So 0 to 1, you have to integrate over 0 to 1. Then product of r of x into w1 of x. This will give you integral 0 to 1. R of x is nothing but t double dash plus t plus x into w1 of x is x into 1 minus x. So dx. So this will give you integral 0 to 1 t double dash plus t plus x into x minus x square dx. Okay, so now we can do is separate the integration. So integral 0 to 1 t double dash into x minus x square dx plus integral 0 to 1 t into x minus x square dx plus integral 0 to 1 x into x minus x square dx. Okay, so first of all we will solve this integral separately, and then these are easier ones, so we can solve it altogether. So now let us consider the first integral. So integral 0 to 1 t double dash into x minus x square dx. So this you have to use integration by parts. So this is second, so x minus x square into integration of second, integration of first dx minus integral 0 to 1. So you have to take derivative of this. So 1 minus 2x into, you have to take t dash of x. That is again integration. So integration of t double dash. So one derivative will be decreased. So it will be just t dash of x. This is over 0 to 1 dx. So this will give you x minus x square into integration of t double dash x. Again it will be just t dash of x over 0 to 1 minus integral 0 to 1 1 minus 2x into t dash of x 0 to 1 dx. So now if we have to substitute this limit, then you'll get x minus x square into t dash of 1 minus t dash of 0 minus, now we have to solve this, so this will be again, we have to use integration by parts in this point, so this will give you first as it is, so 1 minus 2x as it is, then integration of t dash, so this will be t, and then this will be over 0 to 1 minus integral 0 to 1, again derivative of this is minus 2 into integration of this, so this will be t, so again this will be, now x minus x square as it is, now as t equals to 0 and t equals to 0, so at x equals to 0 and x equals to 1, so the derivative will be again 0, so this will give you 0, so no need to solve this, then minus what we have is this, so after solving this for 0 to 1, you'll get 1 minus 2 to integration of 0 to 1 t dx, so final answer will be just minus 2, so entire minus sign is there over here, so minus 2 integral 0 to 1 t dx. Substituting this value of double integral over integral over t double dash x minus x square dx over here, you will get, so you will get I equals to minus 2 integral 0 to 1 t dx plus integral 0 to 1 t minus x square dx as it is, plus integral 0 to 1 x square minus x cube dx as it is, and you have to equate it with 0, so finally you'll get minus 2 into integral 0 to 1. Now we have already considered the trial function t as alpha 1 into w1, right? So and w1 equals to x minus x square, so instead of t you can substitute alpha 1 into x minus x square, so this will give you alpha 1 into x minus x square dx plus, again here alpha 1 integral 0 to 1 alpha 1 x minus x square into x minus x square, so square of this dx plus integral 0 to 1 x square minus x cube dx as it is, which is equal to 0. So now you need to integrate this, so minus 2 alpha 1 is constant, so it will come outside, so integral of this, so it will be x square upon 2 minus x cube upon 3 plus integral, so sorry, after solving this you will get alpha 1 constant and integral of this, so solving this you will get, so x cube upon 3 minus 2x raised to 4 upon 4 plus x raised to 5 upon 5 over 0 to 1, and this will give you x cube upon 3 minus x raised to 4 upon 4 over 0 to 1, and we have to equate it to 0. After substituting this value, the answer is minus 1 by 3 alpha 1 plus alpha 1 into 1 by 3 minus 1 by 2 plus 1 by 5 plus 1 by 12, which is equal to 0. So all of the way solving, you will get to know that it is 3 alpha 1 equals to 1 upon 12, 3 upon 10 alpha 1. So alpha 1 will be equal to 5 upon 18. So now you know the value of alpha 1, so you have t t equals to alpha 1 into w1, and now alpha 1 equals to 5 upon 18, so you can substitute its value, and value of w1 is x minus x square. So now this is equivalent to y of x. So now y of x equals to 5 upon 18 into x minus x square, and thus y of 0.5, which we need to calculate, will be calculated as 5 upon 18 into 0.5 minus 0.5 whole square, and the value is 0.06944. Okay, so now we need to find the exact solution, and for that you have whatever we used to solve in the previous standard, we need to solve it like that. So to find exact solution, the given d is y dash plus y equals to minus x. So now we convert in the form of d, so it will become d square plus 1 equals to 0. So now value of d is nothing but plus or minus square root of minus 1, so this will be equal to plus or minus I. So if d equals to plus or minus I, then CF is nothing but C1 cos x plus C2 sin x, because d equals to plus or minus I. So now to find particular integration, you get 1 upon f of d into minus x equals to, now f of d is nothing but substituting the value of this in the given d, you'll get 1 upon d square plus 1. So the function is this, so you need to substitute there. So d square plus 1 into minus x, so this will be nothing but, it is in the form of 1 upon 1 plus x square. So 1 upon 1 plus x square series can be represented as minus 1 into my 1 minus d square plus d raised to 4 minus d raised to 6 plus up to so on into x, which is equal to, so multiply minus 1 as it is, so x minus double derivative of x is nothing but 0, again this will be 0 up to so on. So final answer is minus x. So now y of x is nothing but c1 cos x plus c2 sin x minus x, that's the particular solution. So now if you consider y of 0 as 0, then 0 equals to c1 cos of 0 plus c2 sin of 0. So this will give you cos 0 is 1, so c1 will be equal to 0. So you got the value of c1. Now you need to substitute this along with y of 1 equals to 0, that's another boundary condition. So after substituting that, you'll get 1 equals to c1, which is equal to again 0, so 0 into cos x plus c2 into sin 1, and x equals to 1, so minus 1. So finally you got c2 equals to, sorry, y of 1 is 0, so here it will be 0, so 1 upon sin 1. So this is the value of c2. So finally y of x is nothing but c1 is 0, so this will get cancelled. We'll be just left with c2 sin x minus x, and c2 value was 1 upon sin 1 and into sin x minus x. Okay, so now we need to find y of 0.5. So this will be equal to sine of 0.5 minus 0.5 upon sine 1. So in your calci, you can find the answer and write it down. So here it is approximately equal to 0.